Hello and welcome to Chapter 7, where we're going to study sampling and sampling distributions in our business statistics course. We're about to enter into the inferential side of statistics, where we start drawing samples from a population and seeing what kind of story they can tell about the population's parameters. And it all starts with the appropriate sampling methods. So in this chapter, we're going to do a few things. Talk about common sample biases associated with sampling, describes several different sampling methods, describe the sampling distribution of the sample mean, which goes a long way to finishing out this course, and explain the importance of the central limit theorem and how we'll use that going forward. And we talk about things like the central limit theorem kicking in, meaning that we've drawn the appropriate sample size. So let's just take a look at this, because this will take us down the road towards hypothesis testing. So let's go back to Starbucks. We had this example before. And they're looking to capitalize on an iced coffee trend, and so they're offering a limited time half-price Frappuccino between 3 and 5 p.m. A certain manager of Starbucks determines that from past historical data, 43% of iced coffee drinkers are women, so the other 57% are not women. 21% were teenage girls, not of the 43% of women, but just separate of itself in its own collection. 21% were teenage girls, 79% were not teenage girls, and the customers spent on average $4.18 for iced coffee, and it has its standard deviation of 0.84. Those would serve as our population parameters. Mu is 4.18 and sigma is 0.84. So what she does is a simple survey. She surveys 50 of her customers and finds that 46% were women. It's a bit more than what she saw before. 34% were teenage girls, was quite a bit more than what she'd seen before. And they're spending $4.26, about 8 cents more per drink. Now, we don't have the standard deviation here. We know the deviation was about 8 cents. So that may not be that different from 418. That's what hypothesis testing will get for us, determining whether or not 426 is actually any different than 418. So she wants to ultimately figure these things out. What's the probability that her customers are spending an average of 426 or more? Are they spending more than the 418? Well, in this case, if she sets the floor at $4.26, she'll say, what's the chance of 426 or more? Again, 46% or more are women, and 34% or more are teenage girls. So to do this, we'd have to go through drawing samples to prove and take a look and see, how do we create probabilities from all of this? Well, let's just start with the idea of sampling. So population, that's everything of interest. So anything that you can think of that surrounds this idea that you're collecting, that's the population. Population parameters aren't always known. In many cases, they're assumed or they're just simply hypothesized. We believe it should be this value. A sample is simply a subset of the population, and a statistic, which is calculated from that sample, is what we use to make inferences about the population and its parameters. So x bar from mu, sigma is inferred from S. Bias, however, is when we look at that statistic and we often tend to have a way to over or underestimate a population parameter. And we realize there's going to be bias built in. And actually, the smaller the sample size does tend to lead to some bias. And if we sample the entire population, we're not going to have much bias at all, are we? Since if you sample the population, you have the population, you're not going to either under or overestimate. So typically larger sample sizes tend to reduce our bias. And we'll see that that's what the sampling distribution of the sample mean allows for. But bias can be a bad thing. Here's one example. During the 1936 election, the Literary Digest, which was a magazine that was read by many affluent folks, they predicted a landslide for Alf Landon over FDR with only a 1% margin of error, which is actually quite small if you think about it. But boy, were they wrong. FDR won in a landslide, and really several things went wrong here. First, there was a selection bias. They're only looking at their own subscribers, which tend to be more affluent folks. And second, they only had a 24% response rate. So those that were opting into the survey, Well, what was their agenda? So we actually committed two kinds of bias, probably more if we look deeper into the study. There are lots of other ones as well. One of the more commonly known ones these days is the idea of a basketball or football player who goes professional, comes out of a university, and from one year the average salary is at a normal rate. The year that they come out, the following year when they review the average salary, it goes through the roof because the salary may go from an average of, say, $50,000 for all majors to $250,000. That's something going wrong when we look at this and we have some bias. But for this case, the selection bias, we're excluding certain groups from consideration. In this case, we're excluding folks that just don't read the magazine, typically lower income voters. And then there's the non-response bias. There's a difference in preferences, and either you opt in or opt out. In this case, we had a low response rate, and only really those who cared about the election took time to respond. That's what is assumed. No one really knows, but that's what's assumed in these kinds of surveys. So we don't know if the responses we got were just typical of the population. There seems to be some bias. We have to be very careful when we sample not to have some kind of bias. We want to make sure that we don't exclude and that we get the appropriate response rate so that we're not showing any kind of opt-in, opt-out desire here. So how will we do something like this? Well, there are several different methods. One of the most common, and it's basically the foundation for all, is something called the simple random sample. Sometimes they call it a grab bag sample, but just think you have a bag full of n observations. Each one has the same chance if I reach into that bag and pull something out. So if there's 10 objects in the bag, even if they're similar or not, if you think of them as distinct objects, just reach in and pull one out, there is a 1 in 10 chance that I could pull out that one observation. Now the problem with this is if we have, say, 10 observations in the 10 objects in a bag, 9 of them are the same and 1 is different, there's a very small chance, a 1 in 10 chance, that I'll pull out the one that's different than the rest. So this idea is not the best because in some situations, we tend to favor those that have a larger populace within the group. Now, most things we do presume simple random sampling, and I'll say that again and again as we go through, but we just have to be careful when we do simple random sampling because what it does, it often excludes underrepresented groups or underrepresented segments. One simple way to do it, just to give you some idea of how to do something with Excel, 1961 students invested 24 hours a week in their academic pursuits. Today, students study an average of 14 hours per week. I guess the big question is, how many hours do you study a week? Well, a dean at a large university in California wanted to know if this trend was at her university. So they've got 20,000 students. Each one has a unique identifier from 1 to 20,000. And just wanted to take a random sample of 100. Well, it doesn't make a lot of sense to go from 1 to 100 or at any point in between within a range of 100 because we don't know how they were assigned those numbers. Let's randomly select them. Let me just take a look in Excel. There's a function in Excel called ran between. There's a lot of ran functions out there, and all I'm going to do is use ran between 1 and 20,000, and I could do that 100 times, 99 times. Do it 100. And so I can tell you that I'm going to pull out person 4407, 14595. Now, this iterates itself and updates. If you hit F9, you can see how they float. The only problem with doing this is there is the chance you could have replicates. Downside to this, Excel isn't the perfect solution for random sampling, but it does give you a nice shot at trying to. For 20,000, if you just pull 100, if you double up there's a pretty small chance of that happening. But so as you can see, it's pretty easy to figure out if you have assigned particular values, in this case values 1 to 20,000, just pulling out 100 can be pretty simple. That would be simple random sampling from that group. Another kind of sampling is called stratified random sampling, where you take the population and we try to cut that population into mutually exclusive groups that aren't so heterogeneous, that they really have a lot of homogeneity to them. They're a lot of similarities within a smaller stratum. So each population has all these stratas. Now that we know we have these stratas broken down, we can be sure, even if we have some stratums individual, value or set of small values in one particular stratum, we can go in and ensure that we'll pull at least one out, and we'll pull out based on the proportion of that stratum size. What this does is guarantees that each population is subdivision or stratum is represented. But once you get inside there, say I have a million observations and I have 15 strata, and what we want to do is take a look at the smallest one, which only has 10 observations in it. That's not a lot versus the million. Once I get down to that level, then I would do simple random sampling within each and pull out a 1 in 10 chance of pulling something out. And we would do it based on its represented sample size. Very proportional, and allows us to make sure at least one observation is pulled from each one of the broken subdivisions. What allows us to do is have greater precision, especially when we go for those that are in the margins. Another version is something called cluster sampling, and what we're trying to do is build mini clusters, each acting like its own little population, very heterogeneous. Once we break them up, and this often happens when you think of voting, and you look into a voting district, how they're broken up, there are many populations, then we'll simple random sample within each one of those. They don't have the homogeneity that you would see within the stratum of the individual stratified random sampling. You would just simply look at them as their mini populations. This is a cheap and easy way to do something. Doesn't have the precision of simple random sampling or stratified, but it's close to simple random sampling. This works best when you have naturally occurring clusters. So again, when you're drawing population districts for looking at elections, is very, very commonly seen as a cluster sample. These groups do not all have to look very similar. They should represent sort of like mini representations of the population for each cluster. When we look at them, cluster versus stratified, stratified is preferred. Usually is the one you would go to if you have the time and money to do it. You're going to get at least one from every group. That isn't true for cluster sampling. You're just taking from each of the groups with the possibility of leaving a particular group out. Precision is stratified. Cost is both in terms of actual dollars and time is clustered. So you can take your pick with either one, but most folks choose stratified sampling within and using simple random sampling within each cluster. So now that we know there's different methods, what are we trying to do? Well, we're trying to look at something called the sampling distribution of the means. What does that mean? Let's just take a step back. We've got this population, and it's being defined by its parameters, mu, sigma, sigma squared. More often than not, when we look at these things, we have no idea what the parameter value really is because you don't know what the population is. Many times the population is ever growing. So you see it as a constant, something you may not even know. It's something that you may just have to hypothesize or guess at. But you know it's close to what you think it is because history or intuition tells you so. Now, each population is going to have its own set of parameters. So for each set of parameters, one and only population. A sample, as we know, being described by statistics, the statistic itself is random and is based on how that chosen sample is put together. We use the statistics to make inferences about the parameters. This is where we get to inferential statistics. We do this, we draw random samples over and over and over again of the same size from the same population, and that's the most important thing. The idea of repeated sampling, taking the same kind of sample in the same method from the same population of the same size sample over and over and over again. If I have a population with 1 million objects in it, I take a sample of a size 100. Just imagine I take one sample, then another, then another, then another, and I do that 100 times. I take 100 samples of size 100. And in the end, if you think about it, you'd have 100 separate sample means. Each one you would hope would be the same and the same as the population mean, but I think we realize that's not the case. What we're doing is creating an estimator. X bar, the mean of the sample for each and every one, is an estimator of mu. Now you're only going to draw one sample, but you have to, in the back of your mind, think this is all about repeated sampling. I have all these means, and imagine if I could take the mean of all the means I just created. So what is the sampling distribution of the sample mean x bar? It's what we just said. Through repeated sampling of the same size in the same manner from the same population, if I draw many samples over and over again, and I take each of those samples, take the mean of each sample, and there's, imagine many samples that were drawn from the same population, many means, and I were to take all of those and build a histogram around it, that's how we would see how these are distributed, much like the distribution we saw before with something as simple as the z distribution or the normal distribution. So when we draw each random sample of size n, we're assuming that we can estimate mu. Now, when we do this through repeated samplings, we're going to get different sample means. We know that. Some may be close, some may even be the same, but across the board they're going to be different, but they're going to be very close. This idea allows us to see how they distribute in their form for these sample means, and the hope is that it has a nice mound-shaped distribution. So here's what I mean. We would take, say, 4 random samples from a population at large. We would take their means, 1, 2, 3, 4, and I'd put them here. And the mean of all these means is the same as the mean of all these because each of the samples is of the same size. They're uniform in approach. So for us, I've just done that. Blow this up a little bit. Here are those samples. I've drawn the means, as you can see, and I've moved the means up here, down below. So if I take the mean of the means, the average of the averages, it's the same as if I took the entire average. So the mean of means is the overall mean. Notice the overall mean of the 4 is 4.557. Here are the 4 means that make it up individually by sample. None of them are 4.557. One of them is a lot more, one of them is a lot less. We're going to have to figure out what happens when we create a mean that's nowhere near what the mean of means is. Could it be an outlier? Could we use something like the empirical rule and say you're more than 3 deviations away, therefore you're an outlier? Well, to do that, we'd have to come up with a z-score. So what we've just done is drawn many samples, in this case 4, calculated their means, distribute those means, see what it looks like. I'll use something called the z-score. Now before to get there, we just assumed that if I had a range of values, I pull one out, I would assume that that value is the mean because, I would draw it once, twice, 3 times, 4 times, take the average of all the different values, and that would give me the mean. The expected value of x was the mean. Same thing goes here. The expected value of x bar is also the mean. Here x bar, here x. They both are considered estimators of the mean. However, this one, x bar, because it's more in its sample size, is going to have more precision, which means less variation. Normally, when we draw this, we would have x have its variance as sigma squared. We would take the square root and create the standard deviation. Now, because we're drawing samples of a size n, we have to account for that and reduce the error. So what we would do is divide sigma squared by n and create the standard variance. Very not well known. We take the square root, we would get sigma over the square root of n. That's the standard error. Standard error is nothing more than the standard deviation of the sampling distribution of all samples, of the standard deviation of the sampling distribution of the sample mean. Standard error, sigma over square root of n, and we'll see later, s over the square root of n as we move forward. It's a very important statistic because it will be used from here on out. We don't draw samples of size 1. We draw samples of size n. N can be 1, but in many cases n is more than 30, and that's an important distinction that we'll see. So what does that do for me? Well, let's just say that I had an opportunity to look at pizzas, and I know historically that pizzas are 16 inches, and they have a standard deviation of 0.8 inches. Where did the 16 inches come from? That's just somebody's hunch, the size of the pan, and the deviation is the same way. Now they went out and draw 2 pizzas as a sample size. From that 2 pizzas, if we assume that mu is 16, the standard error, your sigma, that should be a square root of 4. Square root of 4 into 0.8, square root of 2 into 0.8. We have more precision here. We have less variation about the mean. So in terms of its unit distance away, one being 0.57, one being 0.4, less variation means a tighter fit to the mean. More n, in this case more pizzas, creates more precision. So what we'd like to do then is move this towards z and create a standard normal z-score, but instead of doing it for x and sigma, we'd like to do it for the standard error. The math works out the same as long as you do in advance create the standard error, and it allows for very simple calculations. So, for example, let's just say we've taken many, in this case 13 or 14 samples of a particular size, and we've gotten a number of sample means. Let's just look at this in Excel. What I've done is drawn 14 random samples, and here is the random variable x bar for each one of those. The mean of means would be the average of all the averages. This is your best representation to what mu would be. And what I'm going to do is say this value z, if I take x bar minus what I believe the mean of means to be and divide by the standard error. And I'm going to calculate the standard error just by taking standard deviation of the population for this range and dividing by the square root of n. There's n is 14. And for each of those, I'm creating a z-score. Each one has its own z-score. What I can do here, blow this up a little bit. Each one will have its own z-score. And as you can see, there are some pretty outrageous z-scores here. Here's one that's more than 6 deviations away from the mean. We know that if you're within 1, 2, 3 deviations from the mean, 3 deviations, just about everybody falls within 3 deviations of the mean. The only problem is here's one that's 6. This one outlies the distribution, normal distribution of a mean. Now, that doesn't guarantee that this is a normal distribution. It just outlies where the mean would be. So with that, let's take a look at something like this, where we say, okay, the pizza example. What's the probability that a randomly selected pizza is less than 15.5 inches? Sample of 1 drawn. What's the chance that you draw that one pizza that's less than 15.5? Let's go over here and look at the z calculation. I would take 15.5 minus mu divided by sigma 0.8, and I would get a z value of negative 0.63. Now I'm going to say, okay, 6.3 negative z. 0 is the center, so we know that negative 0.63 is to the left of 0, so it's in the lower 50%. So we know that the value probability has to be less than 50%. We know that it is within 1 deviation of the mean either way. So we know that 67% is what we have in between. So let's just say 34%. We know that it's between, or in the range of at most 34%. As it would fall, it's within that first band. So it's really not that far away. If we do the same thing for 2, and we'll calculate this in Excel in a second, just move that number to 2. Now I'm using the standard error. If you think about it, in theory, this is sigma divided by the square root of n up here, where n is 1. Let's assume 1. Now the p-value becomes 0.88. It moves to the left even more, so there's even less of a chance. You're getting closer to the lower boundary of the first bandwidth of the empirical rule. So how does that play out for us? Let's take a look. So with that, what I'd like to do is use that 0.63 negative. I'm going to plunk it in here to my norm.s. So it's norm.standard.dist. So it's normal, standard, probability. And true means that's the value I'm going to use. It's not going to be just an at value. It's going to be a continuous value. You get 26.4. Now, there's some rounding error there because of this 0.63. It has a lot more digits behind it. More precision allows us to use norm.dist. You put in what your sample would be, population, sigma, true. You get 26.6. There's a 26.6% chance you could draw one pizza and it be 15.5 or less. Again, this doesn't have to be less. It could be less than or equal to. It doesn't matter. It's a continuous distribution because it's assumed normal. The other one, 0.88, same principle. I get 18.94. If I did it here, more precision, I get 18.84. Notice the square root of 2. There's only an 18.84% chance I could go out and draw a sample of size 2 and the sample mean be 15.5. What if I drew a sample of size, say, 100? What happens? There's no chance I could do that. There's no chance I could go out and draw a sample of size 100, and have a 15.5 as my mean. No chance. So you can see that with increased sample size comes power. And that's what this is showing. I'll leave this up for a second so you can take a look at how it also can be done using norm.est and norm.dist, very much like I just did. And again, for the other one, when we draw a sample of size 2, I'm not including the sample for 100, but you get the point. How if we increase the sample size to something quite large, there's really no chance of something happening. And that leads us to the last big piece. Central limit theorem kicking in. Any population that we draw, no matter what, if the underlying distribution is normal, no matter what the sample size we take, we know that the sample we draw will be normal. Great. But with the right size, you can guarantee that the sampling distribution of the sample mean is approximately normal every time you draw. If you've had stats before, normally that number historically has been about 25, at least was for me and many people I encounter. But a better guideline we're finding today with all the precision is a sample size of 30. So if you can go out and draw a sample of size 30 over and over and over and over again, the same way, same population, and take the means or the standard deviations or variances, we'll see we can test. But you take the means over and over and over again, and you distribute them, say in a histogram, it will look or appear normal. So in that case, no matter what the underlying distribution is, you can assume a normal approximation and you can use the z-score. And what happens is, this is just the idea of something would just be uniform, sample of size 1, sample of size 5. As we increase sample size, look how more peaked it becomes, more normal. And if this is the mean in the center, the mean, the median, and the mode would all be in the center. Notice how it's collapsing on itself. And the increase the sample size, the more precision we have, to the point where when n, little n, equals the population size, it'll just be a straight up and down line. The central limit theorem is important to make sure that we can guarantee we have this normal approximation. So back to this original thing, and then we'll wrap up this chapter. This campaign for Starbucks. We knew before she took that sample that historically we believe people spent $4.18 with a standard deviation of 84 cents. Well, this manager, Ann, sample 50 gave a mean of 4.26. The question would be, what's the probability that that sample mean is greater than or equal to 4.26? Knowing nothing about the distribution of the underlying data, only that she took a sample of size 50. What I do is x to the z conversion. I take my x value of 4.26, subtract away the mu. That's what we believe. This ultimately leads to hypothesis testing. Is it really 4.18, or maybe, just maybe, it's 4.26? So in this case, it's more. Standard deviation is 0.84. Take the square root of n, in this case 50, and we get a z value of 0.67. That's a positive z value. It's above 0, so it's going to be on the right-hand side. So looking down from that value, we know that you're not at 1 yet, so you're within the 1 boundary. Since we look back, we don't look to the right, we have to convert this to 1 minus the chance that z is less than 0.67. Take a look at that. So we have 0.67, we have to take 1 minus 0.67, and that's why we take and create, draw this out for you, 1 minus norm.standard.dist, norm.s.dist, take the z value and put in true. You could use norm.dist and put in the values and calculate z for yourself, and that gives you more precision. But we know, based on this, what's the chance that you could go out and draw a sample of size 50 from this population of coffee drinkers? What's the chance you could do that? And the mean from that is at least $4.26. There's about a 25% chance of that. Now, does that mean anything to us at this point? No. But it will when we get to Chapter 9, when we can say, well, is 4.26 really any different than 4.18? We're going to get to that idea of significant difference. Here's exactly what was done, very similar to what I just did. We can see it again, norm.s.dist. If you want to use norm.dist and plunk in the values for what your means and your standard deviation, don't forget the true, because that makes it continuous. You'll get the same thing. Hope that helps. Next step, we'll be moving along into Chapter 8, and we'll start talking about things like confidence intervals.